Great. Hello everyone for coming to CS6101. A quick message from Prof. Min is that he has some issue has to run today, so he's not coming today, but it's fine because the nature of the class is a seminar. So we'll just have our seminar as we have 5 great presenters and we have great audience as have this seminar. The first item to do today is the Kahoot. So who has designed a Kahoot? Maybe you can join it for us from last week's supporters. Who has designed a Kahoot? Oh, thank you so much. So I'm going to yeah.
Do you have the account?
Yeah, I have the
Oh, you have the account.
Please run it for us because you need to narrate a little bit. Yeah, I'm very familiar with the setting up, but please narrate the questions and explain the questions for. Okay. That's it.
So I explained the question.
Yeah, so you can narrate a little bit like what's going on, please answer what, and when we have the answer from the audience, there must be somebody giving the wrong answers, right? And you can explain why the answer is wrong.
I'm not sure.
You're not sure, it's fine. We can learn together. No,
Wait, are you Warren?
I'm not Warren. I'm Yisong. Yeah. I'm from Wakefield.
Oh, okay.
Okay. Please scan the QR and join.
Basically, when after everyone finish the answer, right? Then you see the score, right? Don't press next first. So you explain like why something is wrong.
I'm not sure why. That's the thing.
Okay, I can help.
Yeah.
So I'll just send you.
Okay. Sorry guys for keeping on waiting. I've allowed you in.
How many people?
18. So folks online can also join the Kahoot as we are sharing the screen.
You're being shared.
I don't think you're sharing.
You're not sharing the screen.
Oh,
You need to share the screen first.
Okay, great.
Yeah, you share the screen.
Yeah, also forgot the questions.
I don't think there's more people coming. There are some chats.
Just the author guy.
Oh, okay.
I'm blur the background because you cannot see anything. You want to I'm also not sure. You didn't ask him.
Under video, right? Under video.
Under video. Go under video.
The drop down button.
Yeah, drop down.
Yeah.
There you go.
Oh my gosh. You can change a bit to explain for us.
Okay, we'll just Google all. No, not a problem.
Just ask ChatGPT. It shouldn't be that new.
Right. Shall we?
Anyone join it or anyone else still joining?
I think it's fine.
Do you want to join the quiz?
Kahoot quiz.
Do you
Join
guys
the
want to-
couples, final call.
Give them maybe a minute or two.
No, I'm good.
Oh, bro, it is you. Oh, nice. That's it.
The guy that-
Yeah.
I'm just trying.
Bro, just winging. It's winging you, just winging.
Yeah.
I also winging myself because I actually never do internet boss. You need information on this.
Oh, we are like the middle of the-
Yeah, because he did not sign your purchase list. No.
Okay, so I'm just gonna start the quiz. Okay, it's just a very quick 7 questions quiz.
Yeah.
Okay, so
Yeah, I think it's that. Maybe I want to shift this out so they don't block people. Like just press the it's okay. Oh, take a look. Yeah, just blocking. Need to remove this. Press press that. Oh, I see.
yes, it's not.
It's not.
Yeah, it's not.
The hell? Okay, bring that. Yeah, okay. Oh, sorry, just skip this one.
No, everybody got it correct.
Oh, okay, that's great. So
we
yeah,
don't
we
see
just, yeah. Because prompting is to just provide context to the model. Yeah.
Okay. All right, next question.
So which of the following is not a common use case for prompting large language models? Okay.
Quick. Minutes, 2 seconds.
Yeah, so
All right.
okay.
So someone quick. 2 people.
What was ethical decision?
So, okay, so it's like you cannot ask the model to like solve a dilemma question.
So like it's a bit more complex, I see.
Yeah.
Yeah, okay. That makes sense.
Okay.
What's the primary benefit of in-context learning? Oh, so yeah, actually, why the primary benefit of in-context learning? Why is it enable customization and adaptation to specific tasks, right? Instead of the model performance and okay, honestly, I think it also does improve your model performance. So not really wrong on the yellow one. But for data pre-processing, right? Why is it not true? It's because like this one is after you train the model already and you're deploying the model of inference, then you're prompting the model and then you're putting all the examples in that prompt in order to make the model get a better performance. So you already done the training already. So it's not really pre-processing where that part where the step is under the training step. So that's why the green color is wrong. But yeah, I agree, yellow step should have been correct. Red is of correct, then blue is not really training it because prompting is usually for like inference time, it's not training time. So blue and green are wrong. Yellow is ambiguous, but yeah, red is correct. I think maybe yellow is wrong a bit because it's not as specific as red. I think, yeah.
Definitely red.
I think it's red. Red.
Confirm red.
Confirm red, bro.
So what a hard question.
I wonder. Oh no, it's actually green.
He who's fastest fingers.
Yeah. So now you can describe the volume during the full quiz. Yeah. So what's the limitation of one-shot prompting? So like, yeah, the answer is yellow, right? Because the quality of response depends on the frequency of task. So yeah, those are zero. Okay, based on the lecturers, right? I mean, usually they explain it based on the cost of zero shot. But I mean, when they're doing the lecture, they say that when you give one example, right, it's more specific to one-shot prompting. When you give the example and only give one example, it will tend to overfit more on the example because there's no other context given. However, I think that zero shot, like, because one shot is like a subclass of zero shot, most of the problems from zero shot will still actually be seen in one shot. It's just that specific to one shot is the yellow color one. Yeah. So yeah, now we have or 1 equals 1 is having the most, then Suvin is at second place and Eclora is third. So this question is, after a certain model size, your chain of thought prompt work. Then you're asking whether this is true or false. What the hell is it?
Cute photo.
Is it the Kahoot default?
Yeah.
Yeah, so actually it's true because in the paper or the chain of thought paper, they say that after 100 billion parameters, right, then the model size will work. But I think for like current, like with like newer transformers, right, the actual model limit is getting smaller and smaller because of data quality. When you train on better quality data, so it's like GPT for all, then actually that actually improves the data. So now the parameter size can be smaller and still can perform chain of thought properly. Yeah, that's the last question. This is the last question now, is just reordering the steps of how self-consistency works. Okay.
Yeah, drag the.
Yeah, just drag
objects,
the
yeah.
thing. Yeah.
From top to bottom is the order.
Oh, actually, this one should skip. Yeah. Yeah. So, what do you see?
Yeah, it's
Like this, right? So, for self-consistency, usually you create multiple prompts first, then you generate the responses. Then, because how self-consistency was something like majority voting. So, once you have all these results, right, then you pick like the most common like answer from all the prompts for all the prompts completions, and then that will be your majority answer. Then once you do that, right, you select the best response from there, right, which is like the majority answer. Then you evaluate the consistency. How many of them actually chose this answer? Then from there, you can go on to like extend it to like more other concepts like React, where you choose like, for example, for React, right, they use self-consistency in a way that if it's less than half of the model prompts shows the same answer, right, it's saying that the model is actually very inconsistent and also not confident of the answer. So then you fall back to other methods. Like they use this React method as a fallback method instead of using the chain of thought. Yeah. So yeah, let's check the podium. So in third place we have Equal, right? In second place you have Cornet. And in first place you have, I think it's the 1 equals 1. Oh, you have Suvin.
I think that's right. Thank you.
Yeah. Please also give a hand to Warren for narrating through us, and also Alson, right, for creating this great Kahoot. Please and for them. Okay, let's end the Kahoot and go to the actual seminar for today. Okay, great. So my name is Yisong. I'm the third presenter today. So in our today's seminar, we're going to discuss the representational capacity of different neural architecture. So in our first 3 weeks, we have our intro. We know how powerful the language model is. In week 2, we'll talk about adaptation. And in week 3, we discussed many advanced prompting strategies. But we actually haven't got an idea about what is the underlying model that is empowering these architectures. And so nowadays, NLP seems like a little bit working because we have a running very well language generation model, right? GPT or cloud or anything. But let's think about a PhD student 10 years ago when they're doing their research, what model will they use, right? So they don't have a model that we prompt and have fantastic responses, how they do their research. And so in today's seminar, we're going to talk about this problem. So Yanzhe will go first, talk about n-gram model. So it's something we used for decades before RNN models were covered by Jinjie, and then following by our three peoples in the transformer cohorts. And we'll discuss the transformer basics and some variants and replacement for transformers. And finally, we'll have Kim Thow discussing some philosophical question about what can we actually model. So please welcome our first lecturer, Yinzhe, for discussing n-gram model. Thank you so much.
Hey, so today I'm presenting on n-gram models. So this is actually something that has been used for quite a while actually, like since the I think the first paper on this was sometime in the 1900s or in 1980s, 1990s, when they were talking about some statistical models to model language in the past. But first, let's start with this simple question. What do you think the answer to this is? Refrigerator for one. Okay, anyone else?
Yes.
Yes. Oh, fantastic. Well, yeah, I mean, we all know that the answer is one, me. But how do we know it's me? I mean, we will say, oh, it's common sense. Like, we will think that, oh, just some prepositional grammar rule thing. But how do we actually represent this information in computers? Now, that will be that's the general aim of language models actually, where we talk about the probability of a series of how do I get this? Okay. So for example, if you were to use this context of finding a probability of like finding the next word after is water is so transparent that everyone to find the probability of the word there's this thing called the chain rule of probability. That means that we try to find the probability that this particular word is right after the word is right after the phrase is water is so transparent that. So yeah. Okay, so a simple way to model this is known as the bigram. So this actually came from the roots of the Markov chain, where it shows that if you can technically approximate future events by looking at the nearby events. So this is just we approximate this long context with trying to infer that the word following after that is the word which I think in this context is kind of accurate, but in other contexts it's not really very accurate or very meaningful. So this assumes that we can predict the probability of future unit without looking far back into the past of the context itself. So if we were to generalize this from a bigram, which is known as a 2-gram, or basically the current word and the word preceding it, we can generalize it to become the n-gram, which basically approximates the conditional probability of a word given by using only the n-1 words before. So let's say if it's a trigram or a 3-gram, it will be predicting the future word using only the 2 words before it. So let's say if you were to try to predict the word I am, let's say you try to predict the word from I am, then you'll be, oh, it's Then so in the past they actually use this thing called the count-based statistics, where they actually just count the number of the n-grams in a certain corpus or certain data set, and they normalize it so they lie between 0 and 1 for probability and statistics equations. So this is actually the first scary equation of the day. So we just compute the so-called the proportion of the bigram itself within the whole bigrams that start with the previous word itself. But if you were to actually we actually can realize that if you were to actually observe by trying to predict the next word with the current word itself, you can actually just use this equation. So the top represents the number of words that this specific n-gram appears. So let's say you were trying to guess or trying to get the probability of I am. You can just find the probability of I to find the probability of Wn and Wn-1. And yes. And this is the generalization from bigram to n-gram. So this is the n-gram probability of a word
WN given the context at the right side. So yeah, this is just a formula that describes the proportion of the context given, or rather the context itself given the or the future word itself given the context. So of course we know that not all words will be represented in the corpus itself, and that there are some kinds of permutations that no matter how hard you try to find a context corpus, you'll not be able to find it. So this is also known as a sparse data problem in natural language processing. So we use this technique called the smoothing and discounting approach, where we dedicate a certain proportion of the probability mass function to this unknown context itself, so that we are able to at least allocate a certain probability to this, so that we don't have the problem where we have something times 0 equals to something to 0. And zero in this context means that there is no chance of the probability happening in the first place in a given context, which in this day and age is not likely, because if you were to look at ChatGPT, there will definitely be some person who would come up with a very unique way to ask a similar kind of question that people have asked before. So these are the 4 rough ways: the Laplace smoothing, add-k, stupid backoff, and Neither-Naive smoothing. So the Laplace smoothing is just a very simple way of just adding 1 to the count itself. It's not very revolutionary. Whereas add-k is just adding the multiple k itself. So again, it's like an abstraction. The k it just represents a constant. It can be 3, it can be 5, it can be 10. It's just a constant itself. But according to papers I have read, it does not really give off very good results because of something related to experience and everything. Then there's this very interesting concept known as the stupid backoff. That means that if, let's say, you are trying to predict word after a forward context, like let's say I am walking to the, and then you're trying to predict the word park after I'm walking to the, and you realize that, oh, I can't find the word I am walking to the park. So instead you're trying to predict the context of I am walking to, and you're trying to predict, and you predict the word the instead. And in some sense this works because you are kind of approximating the probability, and you realize that there's a lambda parameter over there to account for the fact that this is an estimated guess. And this is actually this is the approach that Google introduced for their large language model back in 2003 on machine translation. Then lastly, we have this Neither-Naive discounting, which is basically instead of using count-based probability, we look at on how unique this particular term is. So in the paper, in one of the textbooks they used, they were stating how Hong Kong is actually a very common term, but Hong Kong, the word Hong itself is only used after the word Hong, which is not very useful in many contexts. Whereas if you were to use sleeping bed, the word bed itself is used in many different contexts. So it will be given a high probability in this Neither-Naive discounting as compared to Hong for the context Hong Kong. So this is just so this algorithm just works based on the proportion of this context of this word itself. And yeah, and basically the idea is that we want to find the word, how unique this particular word is given the context. And yeah, so you realize that at the right hand side we have this lambda epsilon 1 over v. So this is just to account for out of vocabulary words where we have very unique words, like let's say for example a person's surname, or like a scientific term that is not seen in, let's say, a literature corpus. So this ensures that we will not have this problem known as the out of vocabulary problem, and therefore will avoid the sparse data problem that people back in the days have. But again, we come to this issue of like count-based approximations, because ultimately these techniques, whatever things that proportioning that we're using, they are still ultimately count-based approximations. And another key factor is that we actually use quite a bit of memory if you were to use this. Like, let's say if you were to have W words, let's say if your vocabulary consists of like 10 words, and you are trying to create like 2 grams of this, then you need 10 to the power of 2 grams, which is like 100. It's not that bad, but you realize that you actually go up at an exponential scale. So therefore, there is a need for us to find a way to reduce this memory load or this memory runtime that we have. So therefore, Benju actually introduced this concept known as a neuro-probabilistic language model, in which we take into consideration words of similar meaning, and we should be able to take into consideration longer context without incurring large memory resources. So in this context, we look into this example of how the cat is walking in a bedroom. It's similar in meaning to this sentence known as a dog was walking in a room. So in this case, we know that the cat and a dog is basically just referring to one animal, and a room or a bedroom is just a noun in itself. And was running, is walking, they're basically just verbs or prepositions, whichever grammatical term you want to use. So they should be given a similar word picture vector, and that we should be able to have an idea on, we should be able to make sure that these words have the similar probability function, like these words would mean roughly the same thing. So in the given example, the should be similar to bedroom should be similar to room, and running should be similar to walking. And these are the three layers for this neuro-probabilistic language model. So the embedding layer is basically it's basically a mapping from a word to a vector that describes it. I mean, right now we have word to bear, we have love and everything, but those are trained with the premise of training the embeddings themselves, whereas this is trained with the task at hand of just predicting the next word. So in a sense, this is like the predecessor of all embeddings, whereas the ones that we have are based on more revolutionary methods, probably because we have more compute resources than back in the days. That we have. Okay, then the hidden layer is basically a multi-layer perceptron. So in this paper, they actually explored using hidden layers and without using hidden layers, and they realized that hidden layers actually helps the performance of it. Like if I recall correctly, they used a hyperbolic tensor function, and they used a 3-layer MLP. And the probability layer is just a layer that determines which word is most likely to happen, with a softmax function to ensure that the probability sum up to 1. And they realized that the MLP approach actually helps in terms of like longer word context, and that it actually improves the effectiveness of the language model itself. And this term-wise perplexity can best be described as like how surprised a model is to a data set. So if it's very surprised, then it will not give high probability to the word that it's supposed to predict. Like let's say a model gives a probability of like 0.5, and that's the highest. You will have a higher perplexity as compared to a model that predicts a 0.99 to the same word itself. So the limitations of n-gram-based models is that, as you probably can guess from the word n-gram model, you can only predict nth length models or nth length sequences. So if you were to look at relations that are longer than n-gram, it'll be very tricky for it. I mean, I think there has been work done on like engineering it with like topics and everything, but I think those efforts are kind of hard. Yeah, and it cannot model memory as well as like RNNs or LSTMs later on. And you rely on words co-occurrences within the context window. So there might be, it goes to the previous point where I said that language itself is a creative exercise. There are many ways to describe a similar meaning, and there are many different words to also describe a similar sentiment. And here are some further readings. This is just a pretty nice implementation of the MLP n-gram model. It's done in like roughly 50 to 100 lines. This is the previously mentioned paper I mentioned about split backoff, and this is a very interesting paper about using an n-gram model to classify the grammatical correctness of a sentence. So it highlights the n-gram's inability to capture long-range information. So let's say the book I borrowed from the library is interesting. Most of us will think, oh, the book must be interesting. But surprisingly, the model thought, oh, the library is interesting. So yeah, this is one of the limitations of n-gram models. And I think my next presenter will present on how we can best combat this issue, or not really best combat, but rather an alternative that we can alternative model to combat these memory issues. Yeah, thank you. Any questions?
It's for the embedding layer, right? Like the one they use in this paper. Is it embedding layer the one we use like in learning networks, or is it just like
No, it's just for just for this particular context. So if you based on some reading that I found out, right, this paper, the ones that proposed in this layer, this paper, right, it uses it's an approach that is solely used to train this next context. And the NLP in the middle is not very so-called very deep or so. So my guess is that the embedding layer is not, it doesn't really capture the word vector information-ish. But I will get back to you on a quantitative measure between the embeddings used here and the embeddings used in modern techniques. Any other questions?
check the chat?
Oh, okay, sure. This one. Let me help you with the chat. No questions. Okay. Right, thank you.
Please give Younger a quick time.
Hi, so I'm Jin Jie and I'll be presenting on RNNs and LSTM models, which are sort of like the next step after N-gram models.
Oh, you want to move the chat first?
So we've already seen how N-gram models can be insufficient. And another reason is that primarily human language is not context-free. So we cannot just consider like the words themselves, because the specific order in which the words are presented and the relations between them also encode information. So in this example, I showed her boss, Sarah, in the picture. If you only examine preceding words, you will not know that the pronoun her refers to Sarah, which sort of comes later. So in this case, we use recurrent neural networks, RNNs. So what recurrent means is that some unit within the network, indirectly or directly, takes its own earlier outputs as inputs. So in this case, this allows for the memory which N-gram lacks. So basically, for inference, if you want to map a sequence of inputs to outputs, we need to find the activation value for the hidden layer. And the hidden layer, as a reminder, the hidden layer is the one that sort of like encodes the memory of the words. So this is the activation. This is how you find the activation value of the hidden layer. And after that, you use the hidden layer to calculate the output vector normally. So in this case, the input is a sequence of words, and the RNN will view the sequence of words as a series of word embeddings, where each word is represented by a one-hot vector. So basically, in a one-hot vector, correct me if I'm wrong, you basically have a vector whereby there's only one, and the rest of the values in the vector will be 0. So the output, of course, as with all language models, is the prediction of the next word. And how, in practice, this model will create a probability distribution over the set of all possible words, which is the vocabulary. So at each step, you will use the word embedding matrix to retrieve the embedding for the current word. Then you update the hidden layer, and then the new hidden layer, which is used to which you use to generate the output layer, is then passed through softmax to generate the probability distribution output as we've seen previously. So again, we reiterate that the role of the language model is to predict the next word in the sequence given preceding words. So the n-gram only has the context of size n-1 because that is sort of like the size of your window. Whereas in your recurrent neural network, your hidden state theoretically has unlimited context since it is sort of supposed to contain information about all the previous words in the sequence. But there are also limitations. So in training, backpropagation is used to minimize error. But there's this thing called the vanishing gradient problem, because as the gradients are calculated layer by layer, they will sort of get smaller and smaller. So in effect, your updates to the parameters will become smaller and smaller, and the network will sort of like learn very slowly. So we say that there's theoretically unlimited context, but it's sort of also known that RNNs are unable to make use of information like too distant away from the current point of processing. And the reason is that the hidden layer sort of needs to do two things at once, which is provide information about the current decision and also update and carry forward information about future decisions. So this is where LSTM comes into play. So LSTM stands for long short-term memory. It is not long-term memory plus short-term memory like in human beings, because people have like sort of like multiple modes of memory. But in this case, is the model's name refers to a long short-term memory, which means that a short-term memory which can persist over many time steps, as opposed to a normal or conventional recurrent neural network, whereby due to the vanishing gradient problem, it sort of like diminishes over time. So another solution is to reduce the load on the hidden layer by just adding more elements to manage contextual information. So instead of one hidden layer, now you have one more explicit content layer. And you also have more sophisticated neural units that contain gates. So you sort of like update the model weights more efficiently. So the gates, so how this more efficient updating works is that you will perform a transformation similar to binary masking, in which values near 1 will be left unchanged, but the lower values will sort of become closer to 0. And there are multiple types of gates within each unit. So I'll go through them. So firstly, the forget gate is to delete information that is no longer needed. So in human memory, like people sort of like forget things, to not clog up, to only like to make relevant information be more easily accessible. So in LSTM, how this works is that you compute a hidden weighted sum of the previous state system layer and the current input, and you pass that through the sigmoid function, which is the sigma. And then you will multiply element-wise the mask by the context vector. So you sort of like remove the information from the context that is no longer required. So basically all the low values will basically that will be removed, because that's what that is not less important. So there's also the add gate, which is to select information to add to the current context. So again, you create a mask and then you combine the mask to with the information extracted from the previous hidden state and the current inputs, which is what you will normally do for a normal recurrent neural network. And then that's how you decide what to add the current context. And finally, you add to the modified context vector to give the new context, to get the new context vector. And lastly, there's the output gate, which updates the current hidden layer, which is used to generate the final output. So that's how you get the output normally. So in essence, this is what the neural unit of LSTM looks like, the basic unit. the gates in this diagram, the gates are not specifically defined. So now we move on to the next part of the presentation, which is about transformers.
Questions for Xinjie? Any questions?
No. So, RSTM, RNNs still relevant in visual transformers, I guess.
I mean, if you're asking that it's relevant or not, I guess you can say sort of, because each model that comes after sort of like builds on previous models. So you can see that transformers they sort of like you add additional elements on top of the LSTM models. Correct me if I'm wrong, because I'm not very familiar. Yeah, so you sort of add additional elements on top of LSTM, and so you can sort of say that it's still relevant because it builds upon.
Also, transformers have very high cost, right?
Excuse me, sorry.
Like transformers have ridiculously high cost. So, like if you are doing a university level project, maybe it might be smarter to use LSTM or RNN.
Can ask the transformers presenters to address the question.
I think just like help out your point. I think in the state of like LSTM and transformers, in between there was LSTM with attention, and then that was when the idea of attention of slow economy, and then effective attention.
Oh, you understand.
Yeah. Yeah, no, I'm just saying that like this point of like, you know, one builds on top of the other, like where the ideas are.
Oh yeah, like because
Yeah, I saw like actually didn't appear for me, right?
Great. Thank you, Xinjie. Great. I think we are pretty much on time today. So in the last 3 seminars, we didn't do very well on time management. Today we are doing very good. Okay, so I think we have more time on discussing more about the transformers. So okay, a quick brain teaser. So what is the T in GPT? Oh, great. Yeah, so you know what we are talking about. Okay, so in the part 3, we're going to have 3 presenters. The first is myself. I'm going to discuss Transformer 101. So if you're very familiar with this part, you can have a rest. And after that, Wei Ping will discuss some variants and replacement for transformer architecture. And finally, KT will discuss what can or cannot transformers represent. Okay. So this is agenda for Transformer 101. First, I'm going to have a detailed walkthrough about the transformer architecture. There are 2 components, encoders and decoder. And we're going to have a very specific example about self-attention. And after that, I'm going to recommend 2 readings about attention and before layers. Okay. So as our audience asked, what is the connection between RNNs and transformers? So there must be a cost, right? So like maybe five or 6 years ago, when the people are doing NLP research, we are all using RNN or LSTM architecture, and then a new model came along. So we must ask why, right? So there must be a function why iPhone can replace Nokia's functional phones, right? There must be a reason. Okay. So in RNN, we do the attention, right? So it is a stepwise attention. It means when we decode the n+1 word, it must pay attention or sort of reason upon the previous n words. So why do we need to replace this on step-by-step transduction limitation? Why? Why do we need to replace that?
Because it allows parallel computation.
Great, yeah. Thank you so much, Yanxia, for the answer. So, so the answer is it allows parallelization, right? So it means that previously, when we were doing the language model modeling, or we're in the training stage for for any language model, right? So it must have this step-by-step transduction limitation. It means that like we have a series of words, right, denoted by a block. When we are decoding any block after that, we must have all these three blocks beforehand. So it's the so-called AR thing, autoregressive. It means that we cannot do the training or the optimization of the distribution of the next word prediction in the meantime. We cannot say we have 10 tokens and we do the 10 next word prediction optimization in the meantime. We must do it one by one. So it's a very serious limitation for the previous attention or RNN models. And in transformer, as we can see later, everything is a matrix multiplication, which is suitable for our current hardwares, right? So as people always say, as I quote Steve Jobs, so if those people who really are serious about their software, they're going to build their own hardwares, all right? So it's sort of like we have these GPUs from NVIDIA's in hand, but we don't have a very good idea how to utilize that, right? So in GPUs, we can do matrix calculation and optimization very fast, right? So transformer is a very good way to connect or leverage the benefits from the hardware we have in hand, okay? Okay, so let's have a close look at the actual transformer architecture. We have two parts. On the left-hand side is the encoder, and on the right-hand side is the decoder, okay? So it can be used for sequence-to-sequence tasks, right? So it's like machine translation. As the initial paper by Vaswani et al., attention is all you need. So their evaluation was on a sequence-to-sequence English to Germany or French translation task, okay? And so the actual input is coming from here, is from the left bottom side. We put the word as the input and we guess the input embedding with the positional encoding. So which actually means we also append a information about the actual position of the word in the sequence. And then after a multi-head attention where word attend to each other words, and we after a adding and layer normalization, and then we do another feed-forward layer, and then we feed the information to the decoder. So another question is that, so what is the connection between encoder and decoder? How we connect them? Anyone? How we? Yeah, the cross attention. Could you elaborate more about what is the cross attention?
Not okay, like the QK and B, but I'm not sure which one is from the right, because they mentioned the encoder one, right? Which one is from the Q or K. But you take the outputs from the encoder and then you put them in the attention, then you mix them with like the decoder like values as well, more of the attention blocks. Correct. The exact QK, I'm not so sure which one is. Okay.
So another thing that the encoder has the data representation.
Yeah.
And then you take this data representation and together with the input to it's basically an input and then use input to query the data representation and you get some output.
Okay, great. Thank you, Warren. And your name, please, Nick. Nick. Okay, thank you, Warren and Nick so much.
Query come from the decoder, then the key and value just come from encoder.
Great. Yeah. So, what's your name, please?
T.
T. So T said that the query comes from the decoder, and the key and value comes from the encoder.
Yeah,
right?
from cross attention.
From the cross attention. Great. So, thank you so much for all you guys' answer. And I want to add a little bit on the motivation for this part. So why do we need to do that? So it means like in the encoder we actually have everything in hand, right? So for example, let's say in English to French translation. I don't know any. I don't know too much about French. So maybe we can see je t'aime. Okay, and in English is I love you. Okay, so actually in the encoder we actually have processed the whole sequence about English together, and we keep it as a holistic or everything in hand. We have this hidden representation in hand, and when we're decoding the target language, which is French, okay, and we can refer to the whole English sequence in hand. So it's like it can have a better view about what is going on. For example, when they have the je and dine, and it should output the end of sentence token, right? And then it can just see or compare. So je dine already expressed the meaning that I really appreciate someone, right? So and after it's checking with the source language, and it can say, well, you then already expressed the whole meaning in the source language, and it's done. Oh, please join the center of the whiteboard. Thank you so much, Lawrence, for the input. Okay. And okay, so let's come to the Q3. So which components in the transformer are used by following models? How about BERT? So what is BERT model using? Encoder. So why encoder only for BERT model?
We're trying to encode like the outputs and need to get like the representations. You don't need to decode it into actual words.
Okay, thank you so much, Warren, for the quick answer. So Warren just told us that so BERT actually we only need the representation and we don't need to actually decode the next token out. So we're not doing the actual language modeling, but we're doing mask language modeling, right? Yeah. So in the mask language modeling, we don't actually need to decode the next word out. So we're just using the encoder. So how about T5 model? Exploring the limit of text to text. So what is the next 3 T? Okay, so the T5 model.
Both encoded.
Yeah, why? So why T5 has to use both?
Like the input is sequence and the output is also needs to be a sequence.
Thank you so much. So what's your name?
Jackson.
Great, thanks Jiaxiang for the answer. So the reason is that it is the sequence to sequence text. So we have the source and we have the target. We have to use the both encoder and decoder, and they are referencing using the cross attention to get output. And finally, the star in the room, GPTs. So what is it using? Decoder, right? So we're just doing text generation. It's not really doing the sequence to sequence learning. So we only need a decoder to get the next token out. Okay, so here's a hidden question, which is Q4, right? Okay, so actually in the GPT or any text generation model, we can use it for a sequence to sequence task. Like we can use GPT to do machine translation. And do you guys can think of a technique we learned in week 2 to adapt a decoder only model for a sequence to sequence task? Any technique we can use for that? Sure, we can add an encoder to that, but it's too parameter heavy. Is there any parameter lightweight to do so? Prompt? Yeah. Probing? Yeah. Actually, one thing we discussed in week 2 is the prefix tuning. So we can just add a prefix to the hidden representation to say to guide it, like we're actually doing the task of machine translation. We're doing the task of dialogue generation, right? So this is the technique for the to use a decoder only model for sequence to sequence task. Okay, great. And so after we have this, I think we have a good and solid high level view about transformer architecture. So let's go to the detail or the messy part of the lecture about the math. So in today's seminar, we're only going to cover the MHA, the multi-head attention, because the other components like the feed-forward net and the adding and layer normalization, they're primarily used for optimization issues for stable gradients, and they say in the paper, enhance the performance. So we'll skip it then in class and discuss primarily about the multi-head attention. So as Nicholas has pointed out, so the link between transformer and RNN model from historical view is that they borrow a lot from idea of the attention, right? So how people still in the area of the RNN model are using the attention mechanism, okay? So let's have this example in hand and walk through step by step. it means that after 4 tokens, and we are going to process or predict the next token. Our objective is to have a good context vector, right? But when we are processing the next token, we only have this token embedding, and how can we generate a good embedding condition on the previous tokens, right? So this is the question we ask. So how can we get a good token representation based on the previous tokens? And so we have to do a balancing. We can do it in a very, sophisticated way. Like we built many dictionary and we link something is linked to something. We can build a knowledge graph to mine many knowledge and say, here's a good embedding. But it's not very efficient. And one efficient and good for GPU way is to just do the dot product, right? So, and in this figure, the way we calculate the attention is very standard dot product, okay? And we have the token embedding of HT in hand, and we take the dot product of every token before H1, H2, H3, and H4. We have the dot product in hand, and we take the softmax in this layer, and then all the weights after the softmax will add up to 1, right? Like the n token S has the highest dot product with the first token H, and the very low one with the second token gain, okay? And after that, we can produce the final word representation for this token by multiplying the weights of previous tokens, right? So in this example, we say that the context vector is primarily dominated by the first word, right? H, because the first word H has the highest weight, right? And then we just take the embedding together, right? Okay. Please.
You know, when we are training, right? Intuitively, how do you understand how the model learns what the attention should be?
Okay. So Nick has asked a question. So during the training, how can we actually know what the attention should be? So it's a very good question. I think in this running example, the attention is the actual attention mechanism is parameter free because we use the dot product, and the attention is solely dependent on the word embedding themselves, right? So it's based on the assumption that if a good set of word embeddings, they're good, and then they can produce a good set of attention.
We have to trust the previously trained algorithm.
Yes. Yes. Okay. So this is attention from RNN. Okay. So let's write the equation down. It's basically like we get the hidden state from the decoder. Okay. And then we multiply by the hidden states of encoder, and then we can, and after the softmax, we get attention weights from the each token, and then we multiply to the hidden states of the encoder words. So and again, so the only meaning or the only intention for doing so is to get an aggregate of the context vector based on previous tokens, right? And attention means that which token plays a more important role in understanding the context, right? So it's the linear attention weights function here. Thanks, Lawrence, for the comment. So each gene nach Haus equals to Ivan's home. Okay. And we can very formally write everything down into the mathematical form. Is attention QKV equals to the softmax of this matrix multiplication. And so in the previous paper by Vaswani et al., they call it scaled dot product. Again, so they argue that dot product is very efficient and it works well. And okay, and so it's very straightforward. The only thing we pay attention to is this square decay. So it's a scaling factor primarily for stable gradients. Okay, and so we later will see an example of that. Okay, and then thanks to Jalamer, who wrote a very fantastic blog about the step-by-step walkthrough, we can use his running example to see how the self-attention actually works. So the first step is embedding, right? So it's pretty standard. We have the input queue, input and input key and input values, and we embed it into their matrix representation by looking up in the weights table for that, right? So the first step is pretty simple. It's the embedding. We put the query keys and values into 3 matrices. And step 2 is that we perform the scaled dot product, and the way we perform so is by matrix multiplication, right? So in this running example, we can study like the Q is of the dimension of 2 times 3, right? And KT is the dimension of 3 times 2, which will output a resultant matrix of 2 times 2, right? And then after the softmax, which is still a 2 times 2 matrix, and it will be multiplied to V, which is 2 times 3, and the final resultant output is a matrix of 2 times 3. So Z is the output. Okay. So the idea is still we look up the embedding in Q and K, and we try to assign a soft score to them by who will pay attention to what else. Okay. So let's walk through this running example of the thinking machine. So the idea is that in this sequence, the sequence has a length of 2. The first token is thinking, and the second token is machines. Okay, and we try to compute a resultant matrix by applying self-attention to these 2 words. Okay, so let's remember the sequence of length is only 2. So we have the first step is embedding. Okay, which is the green blocks here, and so we have this the X. Okay, so which is the input embedding, and we look up in the table of the query key and values, and we have the vector or from the matrix of the query key and values. Okay, we have 3 vectors here, and the first thing we are going to do is the scoring, right? So the embedding of thinking, okay, its query is Q1, and which takes the dot product of the key Q1 has a, let's assume the score is 112. Okay, but the thinking, when it's paid attention to machine, it only has a dot product of 96. Okay, so here's the function of the scaled dot product is that we divide it by 8. So 8 is the square of the word embedding, which tends to be 64, right? And then afterwards, we take the softmax between 14 and 12, which is 0.88 and 0.12. And I think Jalamer done a very good job in realizing that, right? So it means that we pay much more attention to the darker color, right? Which is thinking itself, and to the machine. And we have this output of the sum Z1 and Z2. Okay, so it means that when we output the representation of thinking, it means what? It means it largely still comes from itself, right? So because thinking itself takes 0.88 proportion of the embedding, right? It pays very few attention to the machine, right? So it means that from these 2, from this query and key, it means that this set of parameter tells thinking should pay more attention to itself than its surrounding world of machine, right? So this is how the self-attention works. Okay. So after we get one single self-attention of the output out, so the one magic thing in transformer architecture is so-called multi-head attention, and the working mechanism for that is actually very simple. Is that we just replicate the same procedure by k or n times, right? So after that, we get we concatenate them together, and after we do a transformation, and then we get the final outputs of the word embedding. Okay, So one thing to note here is that the actual parameters in between different heads are different, right? So that is to say, this set of parameters are different. So in attention head 1, they have a set of query and keys matrices, but in the in the head 2, it has another set of query and key matrix parameters. So my question is why? Why do we need to set them different? So what's the function for that? Please, Baron.
The thing is because like at least what I understand from the video I watched is so that because like when you got head, right, there's a relationship between words. Then you can, when you split up the multi-heads, right, multiple heads with different dependencies within that relation. So let's say like for when looking at noun relations, then there's split with multiple dependencies, look at like noun, verb, or like sub-nouns and something like that. So that's why I think I understand that.
It's not, I think it wouldn't be more necessarily really split into like,
Yeah,
I think it's more like
it's more like
giving it more chances.
Yeah, it's not a definition of like how like think about it, but maybe it won't be as nice as that. But you know,
Can we say that basically doing a multi-head attention is a parallel version of repeating the experiment multiple times?
It's a parallel version of repeating experiments.
Like for example, instead of doing 8 heads, you can just have one head where you repeat that head 8 times and then you put the data together.
Okay, so Nick just said that. So the multi-head attention is like we replicate the experiments by multiple times and try to see different results.
I know how to like you know how we do the experiment multiple times and then we take the best value to proceed to the next round. So it's something like that. Like you're replicating it multiple times and then taking some weighted average or some aggregated method.
Okay, good. So Nick just mentioned that. So it's possible that we do it in multiple rounds because in the neural network it's a black box. We don't know what's going on, and we want the best version out. So my comment for Nick's answer is possibly true. So it might mean that one set of parameters are trained terribly, but some other set are trained magically, and then we want to use that. I think it might be possible because we have another linear transformation done by the W0, right? So it can serve as the function of selecting the useful information from the, say here 8, right? 8 different heads of attention here out, right? Okay, great. So so my take here is that so my take is a little bit similar to what Warren just commented, which is that different heads might have very different functions, right? So maybe we can think from a practitioner's stand, right? Like so one hand is very, very good for linguistic properties, right? We want to know what is the co-reference, like Yisong is giving a seminar and he's very hungry, so he refers to Yisong, right? And there might be some other heads that is very, very well on numerical calculation, right? So maybe those heads are specialized to pay attention to numbers or something, or name entities. So they're all very valid hypotheses, and we're going to check it later in a paper. Okay, great. So let's sort of call back to our initial overview of transformer architecture. So we have walked through the MHA. So the first question is that in the encoder, are the QKV, the 3 sets of matrices, are they the same? Are they the same?
what do you mean by same? It's like
I mean, they are using the same set of values. Yeah.
Yes, but the weights are visualized.
I think the answer is that they are using the same set of value according to the popular implementation of the Hugging Face transformer. They're using the exactly same set of value between Q, K, and V. So it's the so-called self-attention. Okay, so they are using the same set of value. So maybe we can go back a little bit to the previous slides about calculating the attention in RNN architecture, right? So I think at least for RNN architecture, they are using the very same set of K, Q, and V for them, right? So in this case, okay, the key is the word embedding itself, and the query, which is the contextual word, right? Sorry, I made a mistake. So let me repeat. Okay, when we are calculating the next word, or I mean, when we are calculating the context, right? So the query is a token, right? And the key is all the preceding words, okay? And how we do that is by the dot product, right? So when we are doing the dot product, everything is the word embedding themselves, right? So we're taking the dot product from the green shaded here to the orange shaded here, right? So the keys are the word embeddings, and the queries are the word embedding, and also the values are still the word embeddings, right? Okay, so we can see it here. Okay, so I think for the transformer architecture, at least for the Hugging Face implementation, they're borrowing the same set of idea of the attention, right? Where the key and queries, they are the word embedding themselves, and the values are still the word embedding themselves. Okay, we're clear here. They are using the exactly same set of value. Clear? Okay, great. So the answer is yes. So as for the decoder, are they still the same? I mean, here, okay. So in this, so they have two MHA, right? So in the second MHA, are they still the same? No. So why? Why they're not the same?
But this one, they're just the layer, right?
Yeah.
I think your K, because it's cause attention, it's not self-attention or just for the layer. You're putting K and V from the encoder, and then
Yeah. Yeah, great. Okay, thank you so much, Warren, for the nice answer. I think the answer can be given by a zero QA system, right? So from the figure, we can see that information from encoder is out, right? Please follow my laser on the screen. It's out, okay, and being transducted to the decoder, right? So it means that the query is due from the decoder itself, okay, after its own self-attention, but the key and values, they are from the encoder, right? So please recall our previous example in English and French translation, right? Because we have the encoded or the source language, everything in hand, and we can use that as a set of well-calculated key and values.
When you
Please.
ask, are they the same? Do you mean are they the same between the layers, or do you mean are they the same between the heads?
Between the let me see. Okay, I mean that in one layer, RQ can be the same
Within that same layer.
within the same layer, within the same head. Yeah.
In that case, when you talk about the encoder,
Yeah.
although the Q and V come from the embedding, the encoding layer, but within that one decoder multi-head,
Yeah.
within that, every head in that multi-head is having the same Q here, right?
In the encoder, yes.
Okay, the decoder.
Sorry, but in the decoder is not the case. So in the decoder, under one layer and between different heads, they are having different Qs. Okay. Oh, let me see. No. Sorry, I'm wrong. The query input should be the same, I guess, right?
The query is
Yeah.
from the bottom right, right?
Yeah.
And then the KNV, you're saying it comes from the encoder layer, right?
Yeah.
But within that one encoder layer, the KNV are the same within the layer. It's just that the KNV come from the other side.
Yes.
So that means that within the encoder, they are the same.
Within the decoder, the KNV are the KNV, these two are the same because they come from the encoder.
Right?
Right?
Yeah, they are the same.
Yeah. Can I answer your question a little bit?
Just clarify what you think.
Okay. Okay. So here's a better example to illustrate that. Okay. So during the encoder, okay, we have the self-attention. As we said previously, the keys are the word embeddings. Queries are still the word embeddings, and V's are the word embeddings. So there, everything is the same. But for the decoder, because we have the source to target attention, so the query is different from the key and values, right? Because the key and values, they come from the source language. You can see that the in encoders, the Q's, they are the I went home, right? And K is I went home, right? But as for the decoder, the Q, the query, actually comes from the German sentence, which is Ich ging nach Haus, but the target is the English, right? So I went home. Okay, clear? Okay, good. So maybe for the interest of time, I need to wrap up my session soon, and I welcome Nick to discuss with us offline. Okay, yeah. Okay, and so one final thing about the training of the decoder is that we need to mask something out. So it's a very tricky point is that, I mean, when we are training a sequence-to-sequence model, we actually have the target. The targets of the output in hand, right? So it means that when we are predicting one token out, we need to mask the subsequent tokens out, because otherwise the model can pay attention to these future tokens, which could lead to some cheating during the training, which will hurt its performance, because when they're doing the actual inference, they don't have the future tokens in hand. So here's the realization. It's sort of like we have a we draw a diagonal line in the matrix, and we mask all the upper side out. Okay. And here are two recommended reading for you guys. I'm going to cover one paper by 1 minute for the sake of time. Okay, so the first reading is about probing attention heads. So as we discussed earlier, there are different functions for different attention heads. So in this paper, they did a very good job in analyzing a standard BERT model across its 12 layers. And in each layer, they have 12 heads, which means that there are 144 heads in hand. And they want to know how the heads are functioning, okay? So their methodology is that they use a pre-annotated set of desired property. And in this case, they use example from the FrameNet, and they have this sort of reference chains from the sentence. And they want to study what heads in which layer are functioning that's to link the desired property together. And on the left-hand side and on the right-hand side are two cases that satisfy this property by placing the highest score to the softmax against all the tokens being paid self-attention to, okay? And their conclusion is that there are actually two heads doing the job, and many other heads are not doing the job. And after many experiments, they find that many heads are serving the very similar function, which might serve as a over-parameterization of the model. And also they find that in the lower layer of the transformer, it tends to capture some low-level information like phonology and syntax. And on the higher level, they tend to capture some higher level information about semantics, coreference, which is pretty intuitive. And in this work, and the authors sort of studied the dark matters in a transformer architecture, which is the feed-forward layer, which occupies 2/3 of the parameters of a transformer. But little is known what is happening in the feed-forward layer, because we have a good theory for attention, but we don't know what's going on in the feed-forward layer. Their hypothesis is that they serve as key value memories. So as Yanzhu was talking to us in our first session, okay, we have multi-layer perceptron, okay, and we can write it in this form. So F is nonlinear function, and X times K transpose, which serves as actually the sort of the lookup or the query, right? And V is the value here. And so they place it under this hypothesis and check different keys in the feed-forward layer. and they ask humans to verify whether same keys are serving the same functions, and they do observe similar finding to the previous paper. Is that in the lower layer of the feed-forward nets, it tends to predict some shallow features like substitute some ends with substitutes or ends with something. But in the higher layer of the feed-forward, like in the final layer of 16, I guess it captures something related to TV shows. Okay, and I recommend these two papers too. Any question for Transformer 101?
The RNN attention is different from the transformer attention because I think the RNN is in the hidden state. Then the actual transformer one doesn't use any hidden state, it's just the Q, K, and V.
Okay, great. So Warren asked a clarifying question about the attention in the two architecture. So he said RNN is in the hidden states, and in transformer it's just Q, K, and V. So what do you guys think about his question? So my question to my response to Warren is similar to Nick's answer. All right, so let me speak it out. So during RNN, it still depends on the step-by-step limitation, right? It means that even though I think both are hidden, but RNN is the nth tokens representation is dependent on the previous three, and they have to decode it step by step. But in the transformer, just before everything is, I mean, we can calculate the representation for nth word, even though that's the representation for the previous n-1 words haven't been calculated, can still have that, right? So it can go beyond the limitation step by step. I think both are sort of hidden. We can also say Q can be there a hidden state. Okay. So maybe we can go to our next speaker, Wei-Ping.
Back in week 0, I remember that Professor Michael did something really inspiring. He got a very inspiring speech. And the main takeaway that I had from that is that you can look swag as hell giving a lecture while wearing sunglasses. So I will borrow his look and I will be going through 2 papers. First is RWKV and the second is H3. So how many of you here have read either of these 2 papers? Can you raise your hand?
The second one, I haven't read it.
Okay, I'm frankly disappointed because we have PhD students here. So, okay. So first was RWKV. And you see the word like RNN, right? Like, aren't RNNs obsolete? And you also see NUS. So someone from NUS also did this. So I think that was pretty cool. So the first question is, why would we ever revisit RNNs after we have transformers, right? RNNs kind of suck. So the first problem with RNNs was the vanishing gradient one, which was mentioned previously. If you have to train over extended sequence, your gradient sort of just vanishes, right? And the second one is the lack of parallelization of RNNs. It makes it very difficult to scale RNNs to the degree that transformers can. But the other point that transformers suck is the quadratic complexity, which limits the context length. The main bottleneck of the quadratic complexity is the Q times K matrix multiplication, which is here. When you expand that function, you get that really weird summation with the e to the power of something, and the matrix multiplication is circle. So those 2 are the main culprits of the quadratic complexity. So in previous work, attention-free transformer, there's the link at the bottom there. Most linear attention papers that you will see replace the matrix multiplication with some other function. And in this case, they replace the Q and K with a simple additive W, Ti. So it's actually on the matrix on the left, your left. Wait, that's my left. Your right. Sequence length by sequence length matrix. And the WTI is actually a scalar. The point being that making it additive makes the attention scalable now. It no longer has a quadratic complexity to the function. But the problem is that this is obviously less powerful than attention, right? It's quite similar to word-to-vec in that the representation does not actually change with respect to your context. So yeah, this kind of sucks. So what RWKD did is they replaced weight T subscript Ti with a pairwise position bias with channel-wise time decay vector multiplied by relative position. So all these words make sense individually, but put together, they kind of don't. So what this means is that in the cube over there, you still have your sequence length by sequence length matrix, but now it's actually, W is actually also exists per each hidden state. So in each hidden dimension, you have a unique W. And the T minus I term over there is the time decay. So it actually takes your current position and the word that you're looking back at and says, how far away is the word I'm looking back at? If it's very far away, then your signal actually decays. What I mean is that because this is an exponential function and you have a negative sign in front of it, it actually puts the range of values to like the red box circled over there between 0 and 1. So as it gets more negative, as your relative time decay gets more negative, your W value actually decays to 0. Yeah, so that's time decay.
Excuse me. Can you go back to the previous class? The previous one. I still could not get the main idea here. So
the main idea is to remove Q matrix multiplied by K and replace it with a simple scalar addition.
So what is the scalar addition here? So
it's a sort of like position bias now. The most equivalent would be position bias, but instead of only at the start, you just make it learned and put it in at every layer.
So what is the motivation for putting plus with a scalar?
The motivation is to trade off computational power or representational capacity with the scaling, like make it more scalable, make it less compute intensive.
No, I mean the K. What does K mean?
K is key. You still have keys and values, so K can actually still modify the query, right? Or in this case, query is replaced with weight.
Yeah, so when you plus K with W.
Yeah, so K is actually a vector and W is a scalar. So you just add the scalar to all the values in the vector.
Okay, so what does it mean? So it means that now instead of doing the multiplication Q with K,
yeah,
what you will do is that you add a scalar into the key.
Yeah, and the scalar is learned. So it's, let's say, like this word if you're a token at position 4 and you want to look back at a token at position 2, the corresponding weight there is, let's say, -2, which means I want to pay less attention to a token at position 2 if I'm token at position 4. It's positive, I want to pay more attention to it. So yeah,
I'm trying to get the intuition why they plus.
The intuition is that it works. I am not joking.
It should not be like that. I'm trying to get the intuition why they plus a scalar into the
because
key.
It's more efficient. That's the only answer that I can give you. Linear attention always has a trade-off in terms of approximating a softmax function.
Okay, so theoretically the key means because if you add a scalar to the key, it means that because normally the key would be something like in the dictionary when you have key and the value. So the key would somehow point to the value of, let's say, that token. But now you are changing the key. So I'm trying to
modifying how much weight the key means, how much attention you should pay to this word lah. Because your key is, if it all becomes negative because of the scalar value, then you won't pay any attention to it, right? So that's the intuition. So the
W here basically represent No, it should not be the weight. It should not be the weight. So you say WTI here as a learn scalar. This one is positional bias. You are saying positional bias.
Yeah, usually, yeah, it's similar to the positional bias in the original transform. Yes.
But it should not be the weight, right? It should not be the weight. It should be the positional bias. Okay, so can you come to the next slide? Yeah, I still could not get the intuition, the previous slide, but anyway. So how people compute the W here?
W here, it's learn. The W has like individual W for each hidden dimension, and all of this W is learn.
Individual W for each dimension.
Each hidden dimension, yes. Each hidden dimension is independent.
Okay. So what is T and I?
T and I is the relative position. So T is the current position, I is the position of the token that you're looking back at. Which will
So
make
this
sense.
one is absolute
The
positional.
relative.
And you multiply the absolute position with the W. What is W?
W is just a learned bias, which is the W previously here, but similar function to the one previously here.
Okay, so this one basically means you are trying to multiply the absolute positional difference with a learnable weight. And you are saying that one is the positional bias.
So it's skewed towards recency. The more
Yes, the more recent one,
more
the
focused.
one that's further behind will be decayed and be like have zero contribution to the gradient and back propagation.
In reality, it should not be like that. It should have another way to explain, because if you are saying that the words very far will receive less weight, actually it's not true.
Yeah.
It's not true. That's the point.
Right.
That's why I'm trying to get the meaning of WTI.
What do you mean
here.
should not have less weight?
So it's like a very coarse heuristic.
Yeah,
You're right,
because
it
this
should,
is
but it
RN.
does.
This is more similar to RNNs in terms of attention. Attention, you have very clear, like if you look all the way back and you look at the most recent one, you have the exact same detail when you're looking at it, right? In attention. But in terms of this, they trade off by saying we want to decay and make the ones that are further behind from this token less impact on the current.
What if that token is very important? Like
What if that token is very important? Can I?
Also, that's why like a transformer is still better than other it's the representation capacity. But yes, of course, this is more scalable. That's why
There is trade-off, which is I'm going to the slide.
correct.
Can I?
Yeah, sure.
Okay, I will move on. Okay, we will. There's a question segment at the back. I have a slide for that where we will stop. But RWKV architecture looks something like this. So the R stands for receptance. It's that thingy on the left. It's similar to a forget gate of an LSTM. So it actually has these two equations. So the thing over there actually means the other matrix, the one on the right, which will be multiplied by the output of this R. And the mu R, subscript R, is actually a learned scalar hyperparameter, which, because it's in the paper, they call it a linear interpolation of the previous state and the current state. So remember in the RNN, sigmoid function is what's used for the forget gate. More negative, multiply, it becomes 0, so you forget the state. More positive, it's near to 1, so the state remains unchanged. So what this does is, yeah, it just adds the current state to the previous state. Okay, so at the top is a channel mixing block. So the function at the bottom, right, is the max KT0 squared. It's actually just ReLU function squared. And the entire one over there is what's referred to as V in the here. This is V. I don't know why they use the notation of V. In the paper itself, they refer to a term called token shift, which is passing in the input of the previous state into the current one. So this is token shift. So it runs sort of like an RNN where you pass along the previous output of the layer into this current iteration. Yes, and everything is just multiplied by a linear layer, so there's not really much non-linearities here. So as the name implies, this just mixes channels because that's the function of a linear layer. So,
okay.
Yes.
Can you come back to the previous slides? The previous one. Okay. So so basically, so what is the general architecture? So first it could be the receptance, and then come to the mixing. So do you have any picture like so the general architecture? Okay, so first is the
It runs sequentially like an RNN on the right.
time mix. Okay, so it has time mix first.
Yes,
and then
time
come
mix
to
first.
so where is the recept what the
Inside the both channel mix and time mix has receptance on the left hand side.
Okay, so can you come to the recept? Okay, so here what you are doing is that the key and the value you keep the same, and where is R? Is the receptance?
Yes, that is the receptance. You pass it through a sigmoid function to make it a forget gate.
Oh. So what is the meaning of the receptant here?
It's similar to the forget gate of an LSTM. It decides which of the values of the other matrix that's being passed in, whether it's in the time channel or in the channel, whether it's in time mixing or channel mixing, which one of the parameters do you keep and which one do you forget?
But then in here what you are doing is that you use the receptant to multiply with the key and the value. It means that you are deciding which elements in the key and the values you forget and then you remember and you pass it to the next layer. But the point is it does not directly link to the to the next word prediction, right? In here you are only using the receptive for one computation, right?
Yes, I will get to the part where it passes a state like an RNN.
Can you let him get finished
next
to the time mixing and all those, and there's a Q&A section later, because if not, we are not going to go home until 7
this
PM.
is okay. Let's go to the time mixing block. It's the same three equations where you have like no non-linearities and they are just, and WKV is the function at the bottom. So I think this one is just a terminology thing in the paper. V is the exact, it's also called V, but unlike in channel mixing, this is actually computed independent of K. I don't know why they made this terminology like this, but we'll move on. Okay. So those two terms over there in the WKV are actually the weighted sum. So that refers to the states that's being passed between the two steps of the model. So first thing to notice is that summation doesn't actually include the current token, it's all previous tokens. And it looks VI at the previous tokens. So what this means is that it's actually like a state where you look at basically all the previous tokens and you interact with the current token that you're at. And because there is no non-linearity in these operations, it's actually just a cumulative sum of all previous states. In this case, this cumulative sum can be tracked using a state and passed on to the next iteration. Because of this, you can actually parallelize this like a transformer, because the state is a cumulative sum. Again, you just add it, store it in a variable, pass it on to the next state. So in terms of parallelization, you can actually compute them partially in parallel while you wait for the completion of the first hidden state. This is actually implemented in a custom QDA kernel by the authors, and that's pretty cool. So there's a link over there. Results is that RWKV matches a bunch of these models, but obviously, otherwise they wouldn't publish the paper. And I guess the pros and cons in general is that RWKV has a lower resource usage when actually running inference and also when training as compared to an RNN. And the growth of this RWKV model is actually constant because there's a constant hidden state size, whereas transformers need a linearly growing KV cache to be stored as you decode it. linear context length scaling, and the author says same quality and capability as a transformer model. But the cons is that it's actually very sensitive to prompt formatting and weaker at tasks that require look back. If you consider that you ask a question, you give it a context and then you ask a question at the very end, what is this? But the RNN won't actually be able to answer that as efficiently as if you put the question in front of the context. Because it's just the inherent sequential nature of an RNN, which makes sense logically, right? And I guess on representation, what are the limitations of compared to self-attention, can like the mechanistic limitation of having a fixed size hidden state be truly overcome? The benefits of RNN having a fixed size hidden state is that you can have a lot more computational power at a single step as compared to attention, where you only do like the attention mechanism. But an RNN can do many different operations on that hidden state itself at each time step. So when RWKV implemented weighted time decay, this time decay actually like nearly eliminates the vanishing gradient problem, which means that this can scale to very long sequence lengths. And the non-linearities in the hidden state also helps that. And the second question is the representational capacity as important as like the scalability of the model itself? Because how important was the parallelization and parameter count of the transformers? How important is that compared to your inductive biases of your model? Was the only reason that RNNs couldn't match transformers because it couldn't be parallelized, it couldn't train on as much data as transformers could? Yeah, so I guess that's just the main two questions, food for thought. I don't think we have time to actually discuss these. If this is you, please raise your hand. No hand raised. Okay. Oh my god. Yeah. Questions? No. Okay, no questions. Hand raised, but no question. I can't do anything about that. Okay. The next paper is Hungry Hippos, H3. So state space models are actually a thing which you learn in physics control theory. It actually consists of these two equations. Xt is a state variable, or basically what we consider a hidden state. If you compare it to an RNN, this would be the hidden state. This is like an entirely different class of models from RWKV. So yt plus 1 would be the output. U is the input. And the matrices and the learnable parameters here are A, B, C, and D. So this is a very straightforward sort of like equation of representing different systems and the interactions of it. And actually, the reason why we use this in natural language, in LLMs, actually in neural networks, is that there are three different representations of a state space model. So the first one is the continuous time representation, which is the equation that I just showed you. But actually, this continuous time equation can be represented in both a recurrent form and in a convolutional form, which is actually really cool because the recurrent form allows the decoding. Like if you apply an SSM in the recurrent form to language modeling, you could do decoding recurrently. And yeah, it's kind of straightforward to see the comparison between the equation and the recurrence, right? Xt is the hidden state, which you just pass on to the next time step. Okay, so to turn it into a convolutional form, we have these two equations. So if we want to actually write out x, it would form this series of equations over there on the left. And also, if we want to write out and expand y and substitute in the values of x that we previously computed, we would see that equation. And we realize that this is actually a polynomial. And the du's are actually just skip equations, skip connections, sorry. Yeah, so these actually just refer to skip connections in an actual neural network. And the rest are just polynomials of this form. And this form actually looks really similar to the formula for a convolution. I'm going to pause. Does this make sense? Okay, I'm not going to wait for an answer because that would take too long. Yeah, so basically this equation can be rewritten into a convolution. So Gi is the input and Fj is Ca to the power of Jb. So you end up with having two of these matrices being convolved together, which one is the U, the input, and other is the K, which is something that you can just compute. So yeah, SSMs can actually, using the exact same parameters A, B, C, and D, you can do training in the convolutional form, parallelizable, and do inference in the recurrent form, which means it's more efficient in both. So to evaluate the performance of state space models and its representational capacity, the authors came up with synthetic modeling tasks based off this previous work, Alson, which is called in-context learning and induction hits. They reason that the in-context learning capability and expressivity of a model is tied to the performance of the model on two tasks and its variance. So first task is the induction hit task. And in the table, you see that it actually recall content after a special token. So special token is that little thingy that's not a letter in the induction hit. And in order to recall the token immediately after it, the output will be F. So that's an example of the induction hit task. And the second is associative recall, where you can recall specific key value pairs in the sequence. And so these two tasks are actually really important to your model functioning properly. And the problem was that SSMs lacked representational capacity, at least before the H3 paper came out. So I guess the main takeaway here is that the induction hit and associative recall is basically your representational capacity of your model. If you want to create an architecture that works, right, you have to make sure that it can perform these two tasks. Okay. On the how H3 actually achieved this was to have two state space models so each state space model is actually a layer in the neural network. And first one would be a shift SSM. So what a shift SSM is that it's a matrix of ones along the diagonal, but it's not actually along the diagonal, it's along the diagonal minus one, like here along the diagonal, but not actually on the diagonal. And what this does is that when it actually multiplied with the matrix, it shifts all the coordinates of the matrix down by one, which leaves a space for the output to be added to. So this way it creates like a memory of the previous states. The diagonal SSM is actually based off previous work, so I can't really go into detail, but basically the A matrix defines the interactions of your model. So you actually need to constrain the eigenvalue of your A matrix to make sure that the whole model doesn't explode to infinity. Because this is actually, A matrix actually has an exponential, if you look over there, A to the power of T. So it's actually exponential. So if your A matrix is A to the power of K, can very easily explode to infinity. So if you constrain the eigenvalue lambda between 0 and 1, then your model will work. That's the main idea. Because lambda to the power of K, if it's more than 1, explode to infinity. If it's less than 0, you have random hops between the positive and negative axes. Okay, so that's the main idea. And so how this architecture solves the problem of associative recall is that illustrated here. So in the case of a particular key value pair A and 3, the shift SSM and the multiplication will do like a sort of gating based on whether the previous token was the key. And the diagonal SSM stores the value tree in memory and it outputs it continuously. And the final multiplication will gate whether the diagonal SSM outputs is led through, and it's based on whether the current input token is the key A. If this doesn't make sense, that's fine. Go read the paper if you are interested. Obviously the results are good, right? It matches transformers in perplexity. So the main takeaway is that better synthetic performance actually implies better actual performance, right? So the two in context learning tasks are actually important. So I guess like someone over there in general said, is LSTM, RNN still relevant? Then is attention really the only way of progress? These two models, they are based off RNNs and convolutions, and they both match the performance of attention. So is really attention really like the only way to get better results, better language models. And the other takeaway is when you're creating your own architecture, what must your representation actually be capable of representing to get good results? Okay, so questions. Is this you right now?
Question. Can
Yeah.
you elaborate more on representation capacity and many ways, two ways in which they
Your representation must be capable of encoding the information required to solve these two tasks.
right? What are those two tasks? Well, what are they?
These two, induction hit and associative recall.
Okay, could you explain the table for us?
Okay. Induction hit, the ability to recall a token after a special token is the first one. So the special token is the little, and to recall the token immediately after that will be F. So that's, your model must be able to do that. If you train it for this task, it must be able to perform this task. And associative recall is to recall a specific key value pair. So if you have A2, C4, B3, and you ask for the value of A, it must be able to output 2. And these two tasks contribute to the capability of your model to reason and be a language model.
Why were these two tasks chosen as the definition for representation?
Because
Why not?
previous work stated that these two tasks, okay, so specifically for this previous work, right, in context learning and induction hits, they found that, okay, so in training a transformer models, if you guys have trained transformer models, you'll notice that the loss curve is actually pretty high at first, and then it's a very steep drop, and then it starts to plateau again. So the very steep drop in loss is actually correlated with the formation of induction hits, which means that the model at some point attains the ability to reason about language. And while it's not like this loss is because of induction hits, is that induction hits are formed at the same time as the loss decreases. So it's not a correlation causation kind of thing that we can prove, but it's a correlation at the exact same time, which would seem very strange if it didn't, have a reason, right? Yeah, so if you want to know more, just go read the original paper.
Okay, so like the sharp drop in loss that started retraining, it's correlated but not causal with,
We can't prove a causal relationship.
right, correlated with formation of production.
Yeah, okay. Yes, very interesting. Okay, yeah. Okay, no one's like this, right? Okay. So this is also my cry for help. I don't have a project group. Yeah. Okay, yeah, so that would be me and that would be you dragging me along. Okay, that's my section. Awesome. Oh my god, it's so bright.
The topic that I'm going to talk about today is whether neural language models can represent meaning such that human analogous or human level natural language understanding can be achieved. So the paper that talks about this is motivated by some claims in some papers that say large language models could reason, understand or comprehend natural language or learn meaning. So if you can do all this right, that means you would have achieved human analogous NLU. So the author framed this as the grand challenge in NLP. The author claims that if you have a system exposed to only form during the training, right, it can never learn meaning. They say that genuine progress in NLP, climbing the right hill, not just the hill on whose slope we currently sit. The hill that we currently sit is the large language model hill, because everything is about large language model. And they say that we should maintain some clarity about notions such as meaning and understanding. So we have some definitions according to the paper. So first we have form. Form for us basically is just text or strings of characters. And what is important is the communicative intent. It is something that's external to language. and it is also grounded in the real world. So if you want to understand meaning, right, you need to be able to map natural language expression E to the communicative intents I. And then the second relations here involving natural language expressions E and the so-called conventional or standing meanings S. It's just something that can help you to try and find the correct communicative intent given some expressions. So what's important is to find out about the communicative intent. So the author proposed a thought experiment. So imagine you have two humans, A and B, they're stranded on some islands, and then connecting them is some underwater cable. So through this cable, they can communicate with each other through English text. And then there's this octopus that can tap into the communication, but it obviously doesn't understand English. But because it's intelligent, right, it can look at the communications between A and B, and then figure out some statistical patterns between what they're talking about. For example, if A says something, you can figure out what how likely B is going to reply with something, for example, and vice versa. So after a while, right, the octopus decides to just cut off B and then insert itself to the communication. And then octopus will try and communicate with A, and then A will not suspect that actually on the other end of the line is anything other than B. You will think that it's B talking to him. But eventually, right, A would figure out that actually whoever's on the other side actually don't understand what they are talking about. Because the octopus does not have mappings of words to the real world, it has no way to relate that. For example, one day if A encounters a bear on the island, and then A asks B, hey, can you show me how can I build a weapon that can defend myself? And the octopus will not know what is a bear. Right? How is a bear dangerous? And what is a weapon? Right? How effective will a weapon be against a bear? So it will not be able to give a meaningful response to A. So A will now figure out that on the other hand, this guy actually don't know what I'm talking about. So why did the octopus initially can manage to fool A? That's because partly due to the role of an active listener. Because earlier we talked about how we can find out the correct communicative intent is that you need to make some guesses. So regardless whether some expression has meaning or not, you as the active listener, you will try and make sense of it. So this is partly due to this. And then also the author showed that there are established research that show human children also learn language, not just from form, also they need some grounding to the real world. That means we also shouldn't expect that language models can do the same thing without knowing about the real world. So grounding these representations in model, right, to the real world is challenging. One way that you can do that is through augmentation with perceptual data, for example, photos or other modalities, for example, audios. Right. So if you can augment your training data with some grounding data, right, then you could, to some extent, be able to learn communicative intent. But there are also opposing views and reactions to this paper. Many argue that the meaning of an expression or words can simply be a description of the context in which appears. He argued that if you have access to many expressions, right, or forms, your model could learn some network of connections between them and somehow learn some meaning of it. And he also acknowledged that pre-trained language models today, the word meanings and knowledge of the word are very limited, and you still need grounding. And then there's another paper by Lee et al. That they presented some empirical response to the Bender and Collar paper. They show that language models, right, can learn dynamic representation of meanings and implicit simulation of entity state, even if that model is trained only using text. So their idea is this. On the left-hand side, you have some utterances. You have utterance A. You see an open chest. The only thing in the chest is an O key. There's a locked wooden door leading east. So corresponding to this, right, on the right-hand side, you can have semantic representations of the same thing. A prime. You have an entity chest. The chest is open. You have an entity key. The chest contains the key. You have an entity U and another entity door that's locked. So if you can design a probe, you try to map the representation of language model on the left-hand side to the right-hand side, then you have some evidence that the model can learn some meaning. And then next you have utterance B, you pick up the key. Corresponding to that, right, on the right-hand side, you have an updated semantic representations. Now the chest is being updated to empty. And then it is you that possess the key now. Okay. So again, if you can use your probe to map the left-hand side to right-hand side, you have the evidence. And if your model can do that, right, the next utterance that comes after B, you can rule out already C3. Because C3 is remove an apple from the chest. Because the previous utterances, we never talk about apple. So that's inconsistent with what we have. So that's the basic idea. And this is how they design their probe. If what you're interested in is the door, right, the entity door, you take the language model's encoder, you encode the sentence, the door is locked, to get an encoding. And then you go to the utterance A and you encode, use the same encoder, encode word level encoding. Then you take the door word level encoding. And then here, finally, you train your linear classifier to update W. And then on the right-hand side, right, is your truth value. In this case, it's locked, but you could have lock, unlock, or unknown. And then they did experiments using these two data sets. I will not describe what these data sets are. They are alchemy and text world. And their results is interesting. So they took two encoder decoder model, BART and T5, and they found that they can achieve about 75% correct entity states for the alchemy dataset. And then they can achieve about between 95 to 96% correct entity states for the dataset text world. And then they also compare that with baselines. The first baseline is no change. No change means that when they predict the final entity states, they just assume that the states never change. They take the initial states. So if this is the case, then the probing performance drops significantly. And then another baseline is no LM. No LM, in this case, they just take the most frequent entity state. So in this case also is less performance. And also, they also show that these results here, they want to show that what matters is the pre-training. that makes the difference. Even if you fine-tune this task, right? Actually, the gain you get is very minimal. But what puzzled me a bit here is that why if they take a randomly initialized language model, the performance seems to be not bad to me. 63% to 81%. I don't think they address this in the paper. So if you have some explanations, you can come and talk to me. And here is my summary. So the first paper, they argue that if you have only form as training data, you can never learn meaning. And then they say that human children also need some grounding to learn language. So we also shouldn't expect that our language model can do so if a human cannot. Then if you can augment your data with some grounding data, right? Then you could, to some extent, then learn communicative intent. And Manning took the opposing view. He thinks that if you have access to many expressions or forms, you can also, your model can also learn some network of connections between them and then learn some meaning. But it's a bit abstract. And he acknowledged that the model's word meanings and knowledge of the world are limited. And you also need to augment it with grounding data. And then finally, the Lee et al. Paper showed that using experiments on 2 data sets, you can show that models can learn dynamic representations of meaning and implicit simulation of entity states, even if your model are trained using only text as the training data. So that's what happened.
Questions for Katie? Could you elaborate on what you mean by a semantic approach?
Sorry?
Back when entity
So,
use this semantic approach.
Or semantic probe. This is how they design their probe, right? It's a linear classifier. So with an encoder decoder language model like BART or T5, you just use the encoder to encode the utterance. You encode the entity that you want to model. In this case, it's an entity door. And in this sentence, you want to try and describe the truth value of the entity, which is the door is locked. Then you take the encoder to encode this sentence to give you an encoding. And then next, you use the same encoder to encode in the utterance, right? The first occurrence of door, the entity that you are interested in. You take that embeddings and then you just train to learn the weight of this linear model.
Sorry, I'm still not too clear why the semantic approach is like sandwich. Oh.
Because the decoder gives you the next utterance. So you want to see whether there's some kind of internal representation in the model that can let you map with your world, which is this one.
The semantic approach is one that converts from the embedded dimension to the counter dimension. That's like that layer is like put in the intermediate block instead of one show collapse.
I couldn't really get what.
So like like in a coding decoder, before like after the last block, it's still in the embedding dimension, and then you have to convert, to add a layer to convert it into the vocabulary dimension, right? To get like the software probability. So that we do take that here and put it in somewhere else.
So with this probe, you only need the encoding, the output from your encoder, and then you just use that to train your linear classification. So you will not update the weights in the language model.
So let's say if it was like a an encoder only one, like how is code on if you
If you have encoder only, then your utterance, I think, was just stop here because you cannot actually code the next utterance. So you can still use the same thing. You can, but you have to stop at the first utterance.
No, it's okay.
So let's thank our speakers again.
So overall,
Okay, guys online, thank you so much for joining us today. Thank you so much.
this year is
Thank you.
Everybody.
Sorry, quickly. The last few minutes, sorry, I didn't do a good job in editing my so
I mean, I heard of those papers. They seem not so.